You good? Right. Thank you to everyone who's joined us here today in person and online. It is my great pleasure to introduce you to Dr. Alastair Baker, who's travelled along the M62 from the University of Leeds to speak to us today about one of the national nuclear user facilities called Multiphase, which is hosted at the University of Leeds, and he is the experimental officer for. I've known Alastair for a good many of years now. We've worked together on many nuclear projects, but I believe he's going to fully introduce himself. So I'm going to hand over to Alastair.
Thank you, Catherine, very much for this opportunity to speak to you in person and everyone online and the Dalton Institute. And yeah, I've been lucky enough to work with Catherine now sort of for 5 years in the nuclear sector and on aqueous recycle, but I'll introduce a few of those topics as we go along. So Multiform, this presentation today, the topics that I'd like to introduce is who are we? Some of you may not have heard of who we are. What is an NNUF, or an UNUF, as some people across the industry are calling it now. And then building on to what is Multiform, and then what is the NEG. The NEG is a nuclear engineering group in Leeds that I've got my jumper on today, which I might be taking off when I get a little bit too warm.
Sorry,
hello.
It's not sharing on the.
Oh.
You're on the holding. You're not on the holding slide. You're on the.
Right. Okay. Quickly, come help me.
Right. So
Zoom.
this.
What if I do that? Oh, there's a thing, isn't there? Because I've got it on HDMI. You don't have it's this one, that mirror. No.
Is it just click on the screen?
Yeah. Screen. No. I present view. There we go.
Yes.
You happy?
Yes.
Oh, there we are then. So yeah, and a nuclear engineering group of which Tom in the audience is a member of. So the team, we had the principal investigator Bruce Hanson put forward this grant. He's the leadership, thank you very much for the water, leadership chair for nuclear process engineering at Leeds, as well as the co-director of the CDT Green, which is a centre for doctoral training that followed on from, I think it was Next Generation Nuclear. There's myself. I was appointed as the experimental officer for this facility. So I'm a chemist through training, a chemist through scholarship, and then chemical engineer through practice. I'm also a lab captain for some of the facilities I'm going to show you. Tim Hunter is an academic lead in suspended particles in fluids, as well as the deputy director of the Leeds Institute for Fluid Dynamics, and I'll introduce them a little bit at the end as well. And another person on the team is David Harbottle, who's going to be the molten salt academic lead on this. He's a member of the molten salt, what's it called? But it was hosted here last week in Manchester, and as well as being a co-director for another Centre for Doctoral Training Molecules to Products. A little bit of background to myself. I'm a Welshman who stayed in Wales to do his undergraduate, then taught masters in chemistry for 4 years. In the final year of that, I went into a research laboratory and I fell in love with making small molecules on a multi-step synthesis. So I then went on to do a PhD, part sponsored by the Welsh Assembly Government, part sponsored by a small SME in biotech. And one of my proudest achievements is having written up my PhD thesis, which was quite a challenge, and the link there is at the bottom for those of you who want to download it. But during those processes, I moved from batch to continuous flow chemistry, but I was making really small, really low flow rates. So I wanted to see scaling that up. UK Catalysis Hub was my first postdoc then, or PGRA, or research fellow post, or research associate post. And that was based out of Oxford. The first year was constructing a self-optimizing reactor in the University of Leeds, and then the second year I moved down to Nottingham then, where we were developing bimodal catalysts. So we had ruthenium nanoparticles on silica with an amine on there for turning ethanol to butanol, or trying to. Wasn't a particularly successful postdoc. Then following on that then, the National Nuclear Laboratory then had the National Innovation Programme, I believe it was then, and someone at Leeds put in a good word to Bruce, I believe, and they said take Alastair. So I went from milligrams per minute to millilitres per minute, and then the National Nuclear Lab in the first postdoc then, which was split into a couple of bits of work, which I'll show slides of, went up to litres per hour, which was really, really exciting for me. And I'll talk about some of those reconstructions. And then when I was expecting my son, I needed something longer than a 3-month contract extension. So I took my third postdoc then in the Leeds Institute, I forgot what it's called now, for Textiles and Colour. But the original grant goes back to the Cloth Workers Guild. So this is well, the University of Leeds sprung up around the cloth workers came together and they built a research institute, and the university came around them. That grant is still going, and there I was looking at dissolving cellulosic materials and getting the insoluble dyes off and then respinning those. So if you've ever got any tensile or semi-man-made fibres, that's how we do that. So I was looking at separation and partitioning in that project there. So now coming back to nuclear, just to talk a little bit more depth on what I've done in the nuclear sector then. So in 2018, then I went to work with Bruce, the gentleman on the right-hand side there, cutting the ribbon to GM59, the Hot Nuclear Engineering Lab. And left of me then is Andrew Cowling, our Radiation Protection Manager, and then left of him is our Radiation RSC, Radiation Supervision Coordinator, Chris Bullman, and also the technician for the facility. And a big shout out to Catherine and to Clint here at Manchester. Bruce had the room fully kitted out. It's got the floors that lip up the side, so none of the radioisotopes can seep into the concrete and into the walls. But getting started with all the paperwork, then I'm very grateful for the knowledge transfer that occurred between Manchester and Leeds. From there then, I built the Cascade, pilot plant Cascade of 3 pilot plant centrifugal contactors for intensifying uranium-plutonium recovery, developing the advanced Purex flow sheets with NNL as part of AFCP, the Advanced Fuel Cycle Program. We also, and this is a photo from COVID as we all masked up, we also want to look at the effective size of scale of these centrifugal contactors, because you're going to be limited in glove boxes on how big you can go. If you're going to start developing these at small scale, how do they scale to the large pilot plant scale? So we actually used uranium in all 4 of those contactors. And then finally then in 2022, then I was able to present the results of our work at the International Solvent Extraction Conference in Gothenburg, Sweden. And for any of you starting early in your academic careers, do get to these international conferences. They feel rather like a music festival, which we do in the UK, and you've got clashes of all these other bands that you want to see. And yeah, loads, a great way to get to know sort of where the industry is at. The work that I primarily presented there was the pandemic pursuit, which was looking over the 60 years of centrifugal contactors used in developing flow sheets for the nuclear fuel cycle. And on the right-hand side there was a more UK-centric paper for nuclear futures from the Nuclear Institute, sort of the work that we developed in simulation and in experimentation at Leeds, which is a nice little article on the White Rose repository. And then what I always wanted to do was the effective scale-up, so we did it on residence time and uranium extraction. We looked at then the geometry, shape, and the effect on hydrodynamics and the mass transfer of nitric acid in the TVP Purex system. And then finally then, the question has always been about centrifugal contactors: how do solids behave when they're pumped into these contactors? Do they entrain between contactors in a cascade? And so we're able to prove that. It is a logarithmic scale, but there is cascading occurring of the solids as well as the liquids, which is good. So what I'm here to actually talk to you about is a National Nuclear Users Facility. I believe the way that Sir Robin Grimes told it was that he and 3 other gentlemen had a logo, and then there was a pot of money, and then there were all these facilities across the UK where instead of building up the capability yourself, you could go to a facility and use them. As more and more ministers added their name to the NNUF, then the pot of money got bigger. And phase 1 was then established in 2013, and that consisted of the names on this slide. My name wasn't quite there yet. I was on different, I think I was still doing my PhD at that phase. And then phase 2A and 2B came along, and phase 2B is where we've got Leeds, which was I think the last one to happen. And hopefully we can see a phase 3 and further expansion of these facilities. In terms of Leeds then, successfully had won £3 million for a multi-fluid flow facility. So I'll expand on what that is throughout this presentation. And mainly we want to be understanding the main areas of sort of materials and scale-up considerations across these national nuclear use facilities for the reactors such as JET and STEP. So an introduction now to multi-phase fluid flow. So the liquid of life is water with your proteins, peptides, DNA, salts. In terms of the nuclear industry, you need to be able to have a good understanding of your safety case. Then you can perform some experiments around some of those fringe cases or build up sort of your understanding of the process, and then you can have your models then. So liquids and gases and boiling water, and that's where you sit your boiling water reactors, such as the CANDU Canadian reactor. Where do the solids come into multi-phase fluid flows? We have the degradation in the cooling ponds. Once you take a fuel pin out of a reactor after 4 years, you need to cool it down for a certain period of time to lose some of that heat, and so you can generate some solids there. Gases are interesting. I can't talk at length about this one, but you'd have the plutonium between gases and solids. And then we have an array of other types of multi-phases occurring in the nuclear sector. So you have your high temp, so I don't want to talk about those too much. And then the one that Kath and I are very familiar with, which is organic liquids or solvents, and these come arising from the fuel recycling or moving from an open cycle to a closed fuel cycle. Counting the ball, every time you drop a bouncing ball, counting on the second bounce, counting on the third bounce. The last 2 out of 3 generations, that's been done with solvents and aqueous recycling. So that should give you an idea of where some of these liquids and solids and gases are coming from. Boiling water is one that I've got a really good example for, and radioactivity affects these systems. We've currently not got this, not in a radioactive facility, but we do have that in Leeds, and I'll explore that later. So 14 minutes in. There is a large gap between what we're doing in the bench, in the labs, exploring experimental space, and designing an industrial scale plant effectively. You know, we're never really going to be testing the real materials and the real environments until we've built the actual plant. So we want to be able to compare across these scales, and one of those examples is what I've been experiencing from sort of 16th inch pipe work all the way up to 2-inch pipe work, or 6 mil internal diameter pipe work up to 47 millimeter diameter pipe work. And my friend who works in oil refinery has 8-inch pipe work. So that's what we're aiming to head for. And the NNUF gives you access to experimental facilities to develop these technologies. What we have at Leeds is an actually aqueous acid system, so it's based around dissolving up the nuclear fuels in the last 3 generations of recycle with nitric acid. And we'll also have these new fluids, the 4th generation, where you dissolve it up in molten salts. In Leeds, we have the large-scale water loops in the Sorby lab, which is quite good. And then the way I like to tell it is that computational modelling, you haven't got lead times on waiting on components to come in to build your rigs, to then buy in the materials and dealing with the supply chain. You can change the geometries of your system in silica, and the computer power is getting faster every 6 months. So we're able to take models further than potentially what isn't happening in the real world environment. So we're going to be, I'll show you now how we're going to be generating high fidelity data sets then to kind of help those models come back to sort of reality. And currently, there are no flowed molten salt facilities in the UK. There are very few worldwide. In fact, the one that was shipped to us, they also shipped one to South Korea, but ours is twice as big. So yeah, the molten salts are ours, you'll be seeing pictures of later. So where are we? We are in the School of Chemical Process Engineering at Leeds. For those of you who are in Leeds, we're always giving tours, so please pop in and drop me an email. And again, we're talking about solids, liquids, liquid solid gases, and liquid gases. And we have 3 platforms then. So we have the pilot scale water loop, which can go to 100 degrees. We have the pilot scale molten chloride salt loop, which goes to 550 degrees, and then we have this bank of instruments for measuring fluid properties, which I'm going to go through one by one, at least the big 3. And this system, both systems are representative of what we're going to find at industrial scale. So 2-inch pipe is rather large. The flow rates that we're talking about is 15 cubic meters an hour, 15,000 liters an hour. I think in meters per second is 12 meters per second. So these are really quite large volumes that we're pushing around. So the instrument suite, the thing that I like the most about this is that we have the ability to, we've built a platform that we'll be able to develop projects in-house, but ultimately when we talk to the America, USA colleagues, they can send us a bit of pipe of geometry they would like to see. So we have a 2-meter test section on the water loop. We can further modify that as well to the needs of the customer. And we have reversible fluid flows, changing pipe angles, changing pipe geometries. We have the ability, and that will handle liquid solid gases. We have a FBRM, so that's for particle size and coalescence. And that's then, as you can tell, looking at gases, gas bubbles or solids, solid particles. We have rheometry, so looking at sort of viscosities then if you start dosing in your solids. And then we have an X-ray sedimentation dispersion device, which has already been published in 2 papers, so I'm very happy with that. But the 3 that I really want to talk about, or the 2 I really want to talk about, the last 2 down here. We have particle image velocimetry, which can look at solids and liquids. And then we have Doppler aminimetry, which can tell you about liquids, but also handle the solids as well as tracer agents. So we have a class 4, which is the top class of laser. And the way one of the sales reps sold it to me was that's 4 and beyond, and that includes the Death Star. I still don't quite understand that joke myself. And so we'll be talking about those techniques. So we have access to these. If you want to use these instruments, then we just charge a day rate for that, and we'll just talk with me and the team and see what we can do for you, which is great. So how do we incorporate looking into fluid flows? Real environments use steel pipes, continuously seamless pipes, but lasers need a flat surface. And ultimately, from chemistry, you want to get to equilibrium, you want to get to steady state. In these fluid flows, we'd say a fully developed flow, so no disturbances. So if you have these kind of square sight glasses, then that's gone from a tube to a box, and you're going to end up with sort of eddies and effectively baffling the flow then. So you're not going to be looking at true fully developed flow. So that's a no-go. Another thing that you can get from the brewery industry is these lovely sight glasses from the bottom of your tanks. But this has a curved surface, so that will warp the particles and make them longer, and so that's not ideal either. So what we've gone on to develop, so traditionally then you'd put a box around this, flood it with water, but we're not going to be able to do that in molten salt at about 450 degrees. Okay. That's going to be a spoiler for later, how we get around that one then. Hopefully that slide will be it. So the first technique that I want to talk about is particle image velocimetry. What we have here, we have 2 cameras in stereo. We have a laser light beam sheet going through the middle. We can actually calibrate it against a 3D a 3D calibration target, so we can actually get volumetric flow through this. But effectively, it's stop motion. If you blink your eyes, you can then sort of plot where a particle's moved. That's the Lagrangian particle tracking. That's quite intensive. But for the whole flow field then, if you flip between those 2 images, you can say how the bulk velocity is kind of moved in one direction, start getting turbulence that way. And that would be able to provide velocity imaging for the entire length of the pipe or a specific volumetric cross-section of the pipe as well. The initial limiting factor was the download speed from these high-speed cameras. So if we were to work them at full capacity, providing the highest fidelity data set that we possibly could, that would fill the cameras in 2.2 seconds, 3.6 gigabytes, and then downloading that then was initially 3 times an hour. Now we're up to downloading the data 12 times an hour. So we're able to do lots of experiments then in a single hour, which is really exciting. The system consists of a double cavity laser produced in Leicestershire from Micron Lasers, but the entire system is being produced by the Vision. Can't remember where they're based in the UK. But yeah, very high powered continuous laser. And then we have the 2 high-speed cameras then to be mounted on this mount here. You have the laser there, and you connect the laser with a guide arm then and shine that as a light sheet through your pipe, we have this three-dimensional target here, which I can't, it's not a very good image in the end. But what I can show you here is we have a planar camera setup with an LED light, so we're able to take this around for demonstrations at open days and for engaging with our users and customers. And so what we have here is we have the images being taken in real time. You can flip between the two in stop motion. You can start to see what the turbulence looks like when you're capturing images, but this is actually the turbulence then imaged with my cell phone inside the laboratory then, and then in the daily software then we'll be able to get have laser dot lamimetry, and this technique is absolutely incredible. As I was telling you earlier, with stop motion, you don't know if the particle with static flow is the same particle or particle that's dropped from somewhere else. With this technique, because you've got a fringe pattern of two intersecting lasers, so you send your two lasers, they split down a fringe pattern, and if that will replay, you should the particle drops through there, but because the wavelengths are what's actually shimmering over the top of each other, then you're actually able to stay when you have a static particle in this region. So we have two complementary techniques. We have one technique which completely images the entire cross-section at high flows with the solids, more of the static, stagnant flows. However, this is a small section of the pipe, so this comes with a CNC milling, CNC traverse, which allows us then to raster across the surface like a man with a plough in his fields. We also have a focused beam, I forgot how this is called now. We have our FBRM probe, and effectively we're using this to count particles. We have a little window which is 45 degrees into the flow. Solids hit the window. This goes around, I think, at 4 hertz. And whenever there's a particle on that surface, then it'll count a chord length. You get a mean particle size and a particle count. And we're able to look at bubbles, concentrations of solids. We're currently using it for, we've got one project looking at active pharmaceutical ingredients in precipitation, which is quite nice. And then we can also start to look at more difficult things such as oiling out and the onset of nucleation, which is what we're doing with our pharmaceutical user at the minute. This is how we're going to mount it in our 2-inch pipe. We have a half-inch tapered thread here, and then we just need to mount it all the way back then and clasp on here with a PTFE fitting, careful not to damage the optics inside that probe. And then we can move this probe from the center of the pipe and start talking about the columograph scale. We have the bulk flow, and we move towards the wall. You'll have this sort of viscous sub-region. I'm talking about terms that are more familiar to fluid dynamics, simulations, and I have a slide on capabilities that we have with Leeds as well. This doesn't quite do it justice. I seem to have removed humans from all of my images. I think I come up to about just below the height of this shoulder of the jacketed vessel, which is 257 litres. That can be heated to 100 degrees. We've designed it to work with acids, so we have a scrubbing, we have a condenser, a glass condenser, which the fabricators treated with the utmost care. They don't traditionally fit very much glass, it's all made out of stainless steel. We also have a scrubber there as well to catch any of the off gases of nitric acid breakdown. This is the 2-meter test section. Coming across the middle here, you can start to see how you can rotate this then through 30, 45, 65, and then vertical. To get your fully developed flow, we can spin that side glass around to be in any position, so we can have flow downhill or flow uphill. And in the horizontal section, we have injection. We have baffle ports to take off the University of Leeds' compressed air, and it's not quite the moment to show you the windows yet. So just a quick one on sort of its capabilities, but it's still on the website for those of you who are looking to come and use the water loop capability. I've told you it's got 5 angles, which reversing flow gives you 9 geometries. We can also do localized boiling as well, and we've got some real-time footage from that. We have mass flow, volumetric flow, temperature and pressure measurements as well. And we can go up to 100 grams per litre, which is actually our first chemical commissioning experiment with varieties, a traditional simulant for the nuclear industry, varieties in barium sulfate in water. So this is the very, very exciting one. This is a molten salt loop, known as by Copenhagen as the molten salt giraffe. On this, as I said before, we want fully developed fluid flows. In this case, it's a lithium potassium chloride, a 50-50 mixture. And so going up vertically, we have a 2-meter straight section of pipe, which is very, very exciting. That has flanges, as we had with the water loop, with the brewery industry, with the food industry, with the dairy industry. But then we can expand on this, and we can insert holders for coupons to expose modern-day blacksmith materials to look at their corrosion, or another tube coated with new anti-corrosive materials as well, which is a collaboration that's being started between us and Cranfield University, hopefully. We have an ultrasonic flow meter in there for accurate measurements. It came in 2 parts, and I'm looking forward to telling the story of how we put this all together on another slide. But yeah, we're up to 550 degrees, flow rates of 300 litres a minute, and we've got a particle concentration loading of 100 grams per litre. We've currently just got the 2-angled, but we can have this interchangeable test section on this platform, which I'm really, really excited about. And we're developing 4 ideas inside the Multiform facility ourselves. We're very lucky in the nuclear engineering group in Leeds that we have Professor Mike Fairweather and Dr. Lee Mortimer. A big shout out to Lee for providing me all of these images and all of these words. And what we have down the bottom then is we have a simulation of a fluid flow laden with particles. Then we have a cross-section of a pipe that he's drawn, simulated with the fluid flows inside that. And then if we look at this cross-section, and the thing I like the most is talk about how they actually make up their pipes. You can't simulate every atom in molecular dynamics in a 2-inch pipe, so they break it down into these meshes, into these little boxes then, or 20 million nodes. And on the top left then, you can see 2 balls coming together. That's bulk flow, how they will collide. And as you move further away from the center of the bulk flow, more towards the fringes, where you start seeing the velocity dropping down, you can see the way these particles kind of sluggishly approach each other with increasing Reynolds numbers, I think, down that scale. Right. So some of you may not be aware of what the NNUF or the NNUF is. So by coming to this talk today, or seeing this again online later, the NNUF is a users facility family that was being run out of Oxford. They had a central committee there, and it provides you, the user, access to facilities that then you don't have to build, underpinned sort of for the nuclear science and technology. However, everyone goes to the bathroom and introduces solids to liquids. So I'd love it when the water industry will come to us and start talking about getting high fidelity data sets from our pipe, our water loop system. But there are currently 30 facilities housed across 12 universities, including facilities that you'll get access to at the NNL. There's a radioactive NNUF facility now at Diamond Light Source, which I really, really like. Diamond is an incredible place, and hopefully we'll be operating the same as the way that Diamond operates, or synchrotrons operate. For users who want to come specifically to Multiform, we have 3 tiers of access. You'll come to me, we'll kind of discuss what we're capable of, what the platform is capable of, what we could do to expand and facilitate what your experiment is, and then you can come and run that in. We'll have all the items procured and ready to go. Or we have the ability for you to come in, but just shadow the in-house experimental officer, me or the technician to be appointed later. And ultimately then we have the 3rd type of access, where we agree what the operational campaign is, and then we as the Multiform team will go ahead and collect all the data and then do the data processing and hand that report over to you at the end. Experiments so far, so our particle tracker, as I already said, we've got recrystallization of APIs, active pharmaceutical ingredients. We've got work simulating on the rheometer for sort of crude oil and pipelines. Lee and I are developing the high fidelity validation data set for a CFD model on the mono stage. We also have the hot nuclear engineering lab, which has been added to the footprint of the laboratory space that I'm responsible for. And the water loop has been operated by undergraduates. So I have undergraduate chemical and nuclear engineers now coming in and operating the pilot plant platform that I think we were operating at 8,000 litres per hour, with the agitator and no suspended solids, all the way from startup to completely emptying out the platform as well. So that was quite fun. So on the second half of this, of this presentation. I appreciate some of you, this might not be in your wheelhouse, but I would like to talk about sort of the construction. I came into this project and the project manager, Megan, and principal investigator, Bruce, had been building up all these tenders and starting a timeline to begin this construction. And the amazing thing that I enjoy most about this is that I was able to go and visit all of the companies. They're all based on the M62 corridor. So me coming across to you today is the same as in London, going across London to meet another university. It's just an hour down the road, but at least I get to drive through some green countryside. So our principal chemical engineering firm was Manrichem, and then they had their subcontractors, CE Bennett, who did the manufacturing of the stainless steel and the struts. And then Southern Redford for electricals, and then the lagging company, I wasn't able to get their address onto this. Visual drawing from MULTIform facility from our contractor Manrichem, but that had already been agreed by the time I started. This is what I started to do, which was turned up to an empty laboratory. So we have 69 meters squared footprint, and this is the project manager, Megan. On the, I think it was the 5th of November, we had CE Bennett then turn up and they laid down a bund. Now I've told you this reactor vessel has a volume of 257 litres. Engineering tolerance, you have 10% kind of built into that, just to catch any spills. So that black bund that they laid down first is about, I think, 300 litres, which barely a trip hazard, which is quite interesting. The gentlemen bringing in the stand in the middle with their genie lift. Little funny story about that one. They turned up and they were like, oh, we need to get everything off. But how did you get it on there, boys, with a forklift? Well, we didn't have a forklift truck. So we managed to get it off on the first day. And then with the A-frame, I do have a video of these gentlemen moving it just 5 millimeters to the left, just using the A-frame and 2 gentlemen, which is quite impressive. And then we've changing perspectives then. So on the right-hand side, we've got the flow meter from Romania and the 2-inch pipework coming off that loop. And then on the left-hand image, then you can start to see we still have this blank wall for the water loop. Southern Redfern and RTC Insulation, the electrical and lagging engineers came on site then. So this was it, beautiful, just as the stainless steel. And then we started to clad it and start attaching all the electrical wiring and additional gas lines then, which were installed, which were then connected up as part of the so this is a video from Bennett's, which I'm hoping we'll just quickly, I haven't chopped this in the right. Sort of 2 men, this has all been assembled in their workshop in Brickhouse. And one of the things that I found quite amazing is traditionally in academic facilities that nothing is bolted down, but in their construction phase, I signed the bolt and they drilled that into the floor of their workshop. They just cut that bolt off workshop. Very noisy video showing. You have the static lagging going on being covered, which is shiny, and then we have the black cladding over the top of that then. And then we'll have the electrical engineers now start drilling and cabling up this sort of power control box here for heating up the vessel. There should be another power control box being installed just there. That just popped in, and then you can start seeing all the electrical cabling going on there as well as the lagging bags. Where the lagging blankets, which are not what you find at home, I can detach those and they're around the flanges that we'd like to rotate this pipework through. So lots of different disciplines in on the same day. I think at one point we had 4 different trades in a facility at one time, which was really, really exciting. Then I can get to passing around how would you look at stainless steel continuous developed flows. This is a polycarbonate mock-up. What we have are 2-inch pipework with a lovely flat surface, and this was then fabricated by the University of Leeds' workshop team. He's able to send me a picture of what we have with our quartz blocks. So we have the rubber gaskets they've laser cut. This quartz block has been polished to a high degree, and you can see then how this will fit then into the pipe. These fittings, these holders for these blocks then have been orbital welded at the end of 2 meters, so we have a fully developed flow with minimal disturbance to that pipe flow then to produce the highest fidelity data for those who are looking at that distance. So we're sort of like a wind tunnel, but for suspended solids in pipe flows. The 4 other techniques that I can quickly show that we've got imaging from What we have stabilised here is the surface evaporation. So we have a band heat in Halifax going up to 550 degrees, and we're fully able to stabilise a steam pocket there, which is quite exciting. Small little bits of bubble being generated, so we're able to track from the vision alongside the FBRM probe, alongside the particle image velocimetry cameras as well. And then we have slug flow as well. We completely open up the gas lines from the university's main and we can see the sort of the gaseous phases there. So those are some examples of what we're hoping to start having users on and producing data for them. So we are halfway there, and this is where I start to talk about the molten salt loop. So you can see we have this big gap down the middle, but we have these three cylinders of it's oxygen and moisture that does the water does the corrosion. So we're ready to go. So this is coming out from the other end. And so in collaboration with Copenhagen Atomics, we told them what the footprint of the lab was. We told them how much space, the choke points. And this is Edward House, one of our lead technicians, and the rather strong gentleman that he assembled to get this through from the crate. I meant to add some photos about how it was shipped from Copenhagen through to Leeds, and they had got it down to pretty much the nearest millimetre. We didn't have to take any doors off, which was great, but they did send it with wheels that came up to the side, and those wheels also fell off, so we ended up having to manhandle it with the pump truck. So very, very grateful for that team to get this into place. What we have the two units. We currently have the vertical section and horizontal loop section folded down, and then we have the heater cabinet down here in the foreground. And so then I forgot what the Danish was for a successful erection. But this is now we have Bob Harris and Chris Bullman, and we have Peter Kirby from Copenhagen Atomics. Then they had installed it with a set of potentially single-use hinges, but that went up very, very straightforward. We were able to get to 200 degrees within sort of 7 days of them coming to site there. Right, so that's who we are. That's how we got to where we are as a multi-phase facility. But we are quite a large group in the University of Leeds. All the way through, we've had the logo present. For 4 academics, we have a lot of industrial liaison with specifically with Sellafield. We've currently got 2 master students coming through. We've got 2 excellent technicians dedicated to the hot nuclear engineering lab, and then Tom Robshaw's in the room today, one of our postdocs, and a wide array of doctoral researchers, doing everything from experimentation to modelling. One of the things that I just want to quickly advertise was the hot nuclear engineering lab. Having brought this online in 2018, I'm happy to still see it going, and Catherine and Bruce successfully have got a fellowship out on moving from extracting nitric acid, extracting uranium, to now extracting lithium, which is great. But then the back and forth between me and Catherine, I think it was in 2019, we needed uranium for our experiments, so we set up a supply chain route into Leeds, where I ordered in 2 kilograms of uranium, and then Catherine set up a supply chain to move from Leeds to Manchester. That's been quite successful. We have the pilot scale centrifugal contactor cascade with the multi-scale centrifugal extractor platform. We have one of my favourite clips from a movie. We have a gamma counter, which is in the Somerville theory, so that can tell you from the gamma emissions of an atom, sort of its composition, which is great. We have laser-induced spectroscopy, breakdown spectroscopy, and I know there's a team here in Manchester, so I look forward to discussing aqueous sampling using that technique, and then the kind of traditional stuff. We have spectrometers. We had an acid dissolver with gas analyzer. We have an off-gas capture system, and then we have another solvent extraction system, which the French use at La Havre, which is their pulse columns. So that's a large diameter column. So now, just one last thing as this presentation kind of wraps to an end. I look forward to having a discussion with you and hopefully find some uses. But a date for the diary we have at the University of Leeds is we are hosting the University's Nuclear Technology Forum on behalf of the Nuclear Institute. So that's on the 8th and 9th of July, and that comes with tours of our facilities. So if you want to get your hands on the 2-inch pipe work and see what our instrument suite could do for you, that would be a great opportunity. And it's only, I think, £150. project. We got up to the solid charging ports, the funnels, the tundish, and this is Megan at the end of her time with us, successfully having installed the water loop. So yeah, this is the multiform facility with multiphase fluids in each of the systems, but any fluid in any system. And please think of us as a wind tunnel, but for fluids in industrial pipe flows. We also have in Leeds the Leeds Institute of Fluid Dynamics. We're starting up that collaboration now as well, which is really, really good. A little diagram of a molten salt taken from the LNL's pyrochemistry website. With that, Catherine, I'm going to stop talking. Thank you very much for your attention.
Thank you, Alice. That was a great overview. A lot going on at Leeds, and possibly a lot more if anyone's interested in coming and using the facilities. Does anyone in the room have any questions? Yes.
I have seen in the slides you have reversible flow.
Yes.
How do you obtain?
So that's one of my favourite things during commissioning. That because we at that point only had one glass block. So what we have in the centre here. Still not anything I was starting to. There we go. So what we have is effectively. I'm just going to mute that, and I'll learn that for next time I do a presentation. Yeah, another click. So initially, this was designed to fit into a tool room. So we would have had these pipe geometries then with the imaging window at either end of it, and so that would have gone straight up there, more than 2 meters. But what we have the ability to do here is we can rotate around this spool. So although we have one inlet from the pipe, we actually can divert the flow so it can feed in from the bottom and go up that direction, or we can have it directing and reversing the flow and feeding it down that direction. It was really interesting for me is that when I was revising the answer, talking about it on this talk here, horizontal, there's no point spinning it around and doing the reverse. There's no need. But what was interesting is one of the projects itself that have come to us is they are not interested in fully developed. They want me to create a rig where there's a bulk of solid here, and they want to look initially, put the window down there, and initially look at what happens to applying vacuum to trying to evaporate solids and liquids in industrial pipe flow. So initially, in that talk, yeah, you can't reverse the horizontal, but you can actually use that to your advantage. You can change that position around them to look at the fully developed flow, and it's a case of reversing it downhill or uphill effectively on the same platform. That's kind of what we mean by reversible flow. Yeah. It might be quite a challenge to try and hopefully close the valves in an experiment, perhaps. I think that's probably might be where you were thinking that we could go. We probably need a bit of piping to achieve that, but yeah, good question.
Thank you.
Any other questions from the room? Any questions online?
Nothing online.
This isn't a plant, by the way. So I'm brand new to the University of Leeds, so I don't know any of the stuff that was just talked about. So anyway, Alistair, my question is, this has the potential to be probably quite a long answer, but would you be able to comment briefly on the capabilities of the setup in the context of potentially monitoring an adsorption system, either gas solid or liquid solid? Are there any of the techniques that you've talked about, for example, that could be, applied to such a system? Is what I'm asking.
So is that absorption of dissolved chemical solutes then? Yeah. So you want to put on what sort of at-line sampling measurements then for the solute concentration before and after a particle bed that captures these solutes? I don't see why not. Yeah, you could turn this into a pack. You could put a pack bed column vertically, encased in glass, and bring the imaging techniques up against that. Have sampling ports alongside that, and start imaging the fluid flows and that potentially. I don't see why this platform couldn't do that. If you had a column design ready to go, we could definitely look at incorporating that into our design. running your experiments on this platform, on this test bed, really, at different geometries. I don't know if that's been done before. Or pumping down, that's absolutely, but yeah. It's a, does that really answer your question?
Oh yeah, absolutely, yeah. I suppose the other thing that came to mind is modelling of movement of particles in a kind of a fluidized bed reactor, because you do occasionally get them with adsorption systems in industry, not necessarily in nuclear, but modelling of that sort of process as well. But is that again? Do you think that's potentially feasible, a fluidized bed type interaction?
I'll have to talk to the team about that one. But we have got sort of particles interacting with polymers being developed in CFD in the nuclear engineering group. So we have an understanding of sort of wrapping polymers around solids. But in terms of fluidizing solids, fluidizing beds is one of the projects that might be coming on stream for us as well at some point. So stay with us, Tom. We'll do more work.
I've got a kind of more general question, I guess. You took us through kind of your journey.
Yes.
And this looks to be a long way from those small molecules you were making during your PhD.
Yeah.
I mean, I guess you never imagined you'd end up doing something like this. But we've got a lot of like PhD students, very early careers, kind of listening to this talk. Have you got any kind of like advice for them or key tips you learned along the way?
Thank you, Catherine. It's one of my favourite things to do really is PhDs under the guise of self-learning. You get to choose kind of what you want to be. But the lovely thing about academia is you just get so many opportunities kind of come your way. You have to be so free at the top of your discipline to kind of pick and choose them. Just taking every opportunity that kind of comes to you, make sure you get to conferences, a little bit of sort of structure. I think I got lucky with, I might be biased, I just talk from my experience, but my first draft of my first paper was sort of midway through, so a year and a half into my PhD, and that kind of helped once you had that template of blank tables to fill in, that kind of helped narrow in, rather than sort of Alice in Wonderland syndrome and running down and trying to chase all these sort of avenues there. Just going back up, picking up the main branches and just saying this to treat and publishing, that kind of helped me kind of move along. I'd say, first year, just go away and enjoy it. The second year, just paper and internal conference. And third year, external paper international conference is a really good way to kind of help with mini milestones, but it happened to me by chance, and also attending group meetings regularly, attending seminars to keep your eyes kind of open to the entire universe. I mean, one of the beautiful things I love about the research that we do is that you're the Lord's hands at this point. You're the only person on the planet in the universe putting that specific model system with the room temperature and the space and the gravity. You are right there. So that's pretty awesome. But with sort of how I've gone through transitioning from small molecular organic chemistry to chemical engineering through practice, you just kind of always sort of retraining all the time. You're always learning new things, new software drops, just see projects through to completion. How I scaled up, Catherine, it's kind of something I wanted to sort of do, like working with floppy bits of. I was a chemist initially, so it's like working with glassware, and you see reaction. If you break it, it's brittle. And then moving to floppy tube, and I was like, I kind of quite like this. I like to connect multiple bits together, so I kind of like that field kind of exploded as well once I was there, sort of continuous flow chemistry. But then when I switched over to sort of small scale microfluidics and stainless steel, that sort of transition from sort of being fragile to being able to knock stainless steel around was a lot nicer. So I think that kind of, I don't know, I kind of get passionate, just sort of the little things as we're going along. And just always go to your line manager supervisors with ideas. I think one of the best ones that I ever had was I tried to couple two very basic processes together for 3 days, and I was like, oh, this is going to be great when it works. I had a little reaction going through and then a purification on it, and it didn't work. I knocked on my boss's door. I said, Thomas, have you got a minute? I started drawing it on the whiteboard. And he just turns around from his chair for 1 minute and goes, Alistair, who's going to give you credit for that? And just turns back to his desk. It was a no idea. So I had the chance to play with it, but after a few days, just kind of dropped it really. But a lot of it kind of learning as you go along as well. And for this scale, yeah, just never said no to sort of any opportunities. You know, being invited over to Southern Redfern to do the factory assessment test was just a straightforward yes, but it was sort of expected as well from the project manager that I would be doing that. But yeah, just always take every opportunity, really, Catherine. How about your experience? I mean, radiochemistry and nuclear, it's different. It is the same, but it's a step change, isn't it?
No, my journey to being an academic was also kind of in stages. I didn't start in nuclear. I had no aim to end up in nuclear, but again, it was taking the opportunities, using my skills, kind of to gradually progress as I went through. Yeah, take what skills you have, see if they can be applied to different areas, and then gradually start having a wide range of areas that you can draw on, and kind of then create your own little niche. But also, if you're going into a new area, don't be afraid to ask the stupid questions. Like, you don't know. Reasonably, they cannot expect you to know when you're brand new to the area. Ask the stupid questions, otherwise, who knows? You could be 5 years down the line and still not have any idea. That's what I always recommend as well.
Yeah, polymer chemistry was the worst, and I started just emailing authors of papers. I was like, this is the hardest thing I've ever done. And then the dye stuff. I mean, dyes have been around for 2,000 years, and I found someone who was an expert in that, and she gave me loads of time to find the right sort of people. Was another thing to kind of speak to her on. With that, the digital first approach, I think when I was in the lab on my own in 2015, I got big into developing sort of my professional footprint on Twitter, which is now gone, sad time. But like, if you kind of build your own sort of digital profile as well, that's another way to kind of have another network and sort of get information that aren't just within your research group or your university or your country. So yeah, that's something I've been I quite enjoyed actually. It's having a sort of a wider network, which is outside of kind of the academic where I sometimes found myself in the PhD. Yeah, good question. I like that best. If anyone wants to talk about the PhDs first, second, third year, I've got time after this. So yeah, I'd love to.
Yeah.
So I have a question about some of the imaging techniques you mentioned. Like, for example, the PLA. I'm a bit outside this field, but I've done a little bit of PLC. Are you looking to apply that in the Molten source now?
Yes. Possible? Yes. Good question. So, particle image velocimetry. What particles are you imaging? So in the acid system, it's a polyamide bead, 20, 60, 100 microns in size, and that has the same buoyancy as the same sort of density as the water, so it kind of flows nicely through that system. For molten salt, you expose plastic to that, it's going to burn, melt, combust. The system that we have been told that our collaborators would move to, and the supplier of the system, Dantec Dynamic, glass beads coated in silver. And so the laser will flash off those, and then we'll be able to capture the particles and imaging that way. How we're going to build in the sapphire window, similar to the block that you've got here, in talking with Copenhagen Atomics, is we're going to have sort of furnace glass building out longer and longer from that. And then either having fiber optics coming as close as we can through this, but that's sort of all in development in sort of our team and with users really in our collaboration with Copenhagen Atomics. But that's the particle image. It's glass coated, silver coated glass beads. Glass beads coated in silver. Yeah, how we're going to get the cameras closer to 500 degrees. It's going to be a bit more that's more of an engineering challenge than we're developing in-house. That's why, from the diagram, really sure that we saw, they are quite chunky holders that we had designed on there, and that's because we're straight away designing to work on a normal salt platform, how we'll hold the sapphire window in there. In terms of how we're going to get the cameras and stuff, that's going to be developed. But there are techniques, PID is used in combustion, in looking inside combustion engines. So you can't get two high-speed cameras at a distance in, but there are techniques that we're developing. It's a good question, thank you.
You talked about your molten salt rig.
Yes.
Showed your argon bottles.
Yes.
To get the oxygen out of the system.
Yes.
How are you drying all those salts before you put it in? And how dry does it need to be? Basically, stop the corrosion from taking off and when the pile of dust on the floor, or if you're bummed or whatever you've got there.
That is an excellent question.
Good, thank you.
Thank you very much. So, for those of you who spend time at the seaside, salt water corrodes everything. but it's not the salt on its own, it's the moisture, more specifically it's the oxygen providing electrons. So the UK government has revised down, I believe, wind turbines at sea from 25 years to 15 years because of corrosion. So in a molten salt rig, where it's salt, you don't want to have that corrosion happening, so you want to remove that water and that oxygen. You just don't want that. That's where the corrosion, that's something we want to look at, how that gets in there, but ultimately we want to operate this as in nowhere else in the universe. Humans have this amazing ability to create a new universe which is not filled with space. We can do vacuum, we can do under nitrogen, but to fill a pipe system full of argon, that is completely unique to man-made, right? So we have a dehumidifier circuit, so that reduces our argon. So one thing you can do is you can constantly blow through argon. And so then any water that is in the insulation gets liberated if you heat it up and you blow that off. You can cut that down by trapping it as a solid, so you can have a freeze trap. So that does the oxygen, that does the moisture, and the oxygen is to be blown out effectively then. So that's purging it through with argon on multiple cycles then. And then, yeah, we want to keep that as low as possible. So inside we have a humidity sensor with an oxygen sensor. I'm not sure what I'm allowed to say with regards to Copenhagen Atomic's operating conditions, but they have tolerances and limits on how low they can go. In terms of how dry the salt was inside when they manufactured it, and then their technique of putting it into this salt loop smelter. I've seen it. I have a copy of the ICP results for that, and it is. I'd love to know how they make their salt. So it's like their company. They have a way of making the salt very, very clean, very, very dry, very, very devoid of sort of impurities and oxygen, which is quite impressive. So that now sits in the smelting side of our molten salt loop, which was then capped off. But then when we start heating it up again, we'll have to remove all the oxygen and moisture because we took off the front panel, so it was exposed to atmosphere. So we do have moisture and oxygen in there. So we are currently purging that through with high flow argon.
So it came with a pre-filled salt package, basically.
From their factory, yeah.
Right.
Yeah. Yeah, it's the same as when you take when you go to the supermarket, you get a bottle of bleach, sodium chloride, you've got a cap on it. So I think that's how it shipped to us. Yeah.
Maybe another great, well, another one, on your plus loop. You see any corrosion with your beads that you're blasting around your system?
That is an excellent question, and if I had brought my notepad to write it down, that is something we should definitely try. Yes, so if you're blasting them around at such high velocities, what's going to happen to them, especially with sort of some of the geometries we have in here? Yeah, I think I should keep an eye on that one, absolutely, and we'll just run that on our FBM probe offline and through the master site to see if there's any degradation at those sort of velocities. That shouldn't be a problem. The interesting thing about it is that we're not going to, this was initially designed to be 5 meters up in the air. We've lost 5 meters of headroom. There's a story behind that, to having a pub. But we have below it a gravity separator, and so that's got 3 baffles in, and so we just let the partial of the tank decant, and then we tap off the supernate off the top there, and then scoop out after a certain while, we scoop the solids out, so we're not discharging any plastic out to waste then. We're also not discharging any nitric acid. We'll do the neutralization inside that tank where we have a pH probe as well, so we can monitor the change in acidity, so it's then suitable for discharge through the system.
Is it quite a high concentration of beads you've got in the system? Or, you know, is it, I'm sorry,
no, that's good.
If you see one, you know, there's one here, or is it always you're pushing around almost like a slurry of material?
You can't image the slurries.
Right. Okay.
So that is there is a limit on dosing that. So that's done manually. In terms of imaging a slurry, then you're sort of looking at 2D with a high-speed camera rather than the volumetric method with the PIV stereo system or with the LDA. The LDA, no, because you're going to have lots of part. LDA maybe. I'll have to look into that one. But it's a good question. But yeah, PIV and LDA are low concentration particles. But then we are doing 10 to 8%. I think it's glass beads in the system. So we will be doing that experiment, but imaging will probably do with high-speed camera for that.
Sorry, it's a bit of a question. It was a question from my past, but life or whatever, where I was doing erosion corrosion gas systems. So
yeah,
I was just interested what you sort of think you're getting here, that's all, so.
Yeah, the corrosion erosion, there's a very good set of YouTube videos from the US Chemical Safety Board about vents that eroded and then split, and then it was a £10 million oil spill at their refinery. So the Americans want to send us a cracked or a bent piece of pipe that has eroded. So these are, if you want to look at that again.
Right, so I've got bits of eroded material, I've got a piece of my office stainless and take mil thick.
Yeah.
It was from a cat cracker plant.
Right.
Okay, and it went through it in 3 months.
Wow. Wow. For
Let
those
me show you before you go over.
Yeah, for you guys who don't know, cracker plants are sort of, crude oil is the only sort of product that comes when you turn it into, it's the only product that makes more products. And the primary way of doing that is through what's the cracker for snapping C12 into shorter bits. That's gone through quick, that. Yeah.
Yes.
Yeah, it's gone through quick, that. Thank you. It's great to have oil and gas discussed because food safety is wrapped in plastic, drugs are made out of it, everything's made out of it. We just need to stop setting fire to plastics.
Yeah.
But I think it's 10, 20 times more produced than iron. So you can recycle the iron in a molten salt system and cut down on energy emissions like that. But, yeah, we're always going to need oil and gas. Sorry, Catherine.
It's all right. No, it's good that there's a discussion, but I have no idea what the time is, but I imagine it is probably time to wrap up.
Good time, yeah.
Yeah.
Well done,
So
Catherine.
thank you again, Alastair, and thank you everyone who's joined us in person and online.
Thank you very much. There's also plenty to that, so if anyone would like to take off.
Oh, that's sweet.
You're very welcome to.
Oh, thank you very much. Thank you very much. Oh, Jamie. Oh, right. That's your Jamie.
I'd say